Okay, so hope you all had a good lunch and get some coffee or tea to go with the class, right? So now you're home, you can have food when you're sitting in class. Don't fall asleep. I can't see any of you, so I'm hoping that you're all there. Um, so we'll start from where we left off, right? So we're looking at variance in the last class, and the last thing we said was you can start doing recursive variance. Essentially, the variant types whose constructors, the values in the constructors, the types in the constructors refer to the type being constructed, right? So here is an integer list where you have a nil and a cons, and cons is essentially similar to your node in a linked list where you have the value and the next node, right? Next node is the same type. So you can keep building conses, and the last one will be your inul value. So inul is a list, and icons is values of constructors icons is also of type int list. Okay, so they should give you the usual expected result, right? So the type is being inferred here as automatically to be int list. And the terms nil and cons originate from Lisp, right? So we just use it whenever we build lists in functional programming because um, Lisp is sort of one of the father of all of these ideas, right? We sort of borrow ideas from there. So we tend to use nil and cons. Yeah, okay. So now let's build a different list now. Let's build a list of strings. So each data item in the link list is going to be a string. So we define a type string list. So snil to be the end of the list, the terminator, right? And scons to be the cons operation for the list, which constructs a node which contains a string and the rest of the list. Right? So, but you can sort of see the problem at this point, right? So of course I built int list. Then you can ask me. Then I showed you string list. But what about arbitrary types, right? So what about float lists? What about point lists? What about shape lists? Because OCaml allows you to create your own types, there are infinitely many lists that you might want to describe, right? But if I ask you for say the length of a list, the length of a list is a property of the structure of the list, right? Not anything about the content of the list. So you should be able to sort of express these sort of properties which don't appeal to the values that are contained in the list. So far, in all of the examples that we've seen, we've never had this issue. And this issue is very common, right? A lot of languages have this issue. They solve it in different ways. And the way we sort of express these sort of lists that are parameterized by different types is this syntax. Let's first focus on the syntax. This sort of ties into the idea of parameterized variance. Let me dive into what it is first. So we still have the type, right? We still have the type name list, but there is this new thing that is sitting here, right? It's quote, character, and then a, right? And this quote a is sort of describing a generic list, right? And this quote a is a placeholder for any type. Just think about that as a placeholder for any type. And now what we're saying is this parameterized list type, where the content could be of any type, right, is constructed this way. It has a nil constructor, which signifies the end of the list, and it has a cons constructor, which constructs a node in the list, where the content is of the same type, right? We use the same name quote here, and the rest of the list, the tail of the list, is also going to be a quote list, a list of the same type. So let's look at examples. I think this is just the syntax, right? So the way you should sort of see this is these are just placeholders, right, for actual concrete types. And the way OCaml sort of writes down the type is exactly the same as what we've written down here, right? Now you can use these constructors in order to construct actual lists. So let me come to that question just after I explain some of what you can do with this. So here is, I'm using cons and nil from here, right? I'm not using icons. That's the difference here. So I'm using cons and nil, right? I'm actually using 1 and 2, which are integers. So if I run this, the type that OCaml infers for this list is going to be an integer list, right? And the way it inferred the type is because the type of the value that I store in this list is a integer, right? And the type of this is replaced with wherever alpha occurs here. So it expects that this is of type integer, and the rest of the type is also an integer list, and the whole list is going to be of type integer list. Okay, so it automatically infers that it is an integer, and similarly, you can do string here, right? What it's doing is it is looking at this list, and because you've used string here, it is inferring that this list is going to be a string list, right? So observe that we have not specified the type, but OCaml automatically infers the type, and we are using the same constructors, cons and nil, for two different kinds of lists, right? So this particular construction is generic over the type of the actual values that are contained there. The thing that you cannot do here is I cannot do something like this, right? This is a problem because the way OCaml, let me come to the questions just after a minute. So the way OCaml sort of infers the type of this is it looks at cons, right? And cons is this constructor, and it says, okay, cons has this placeholder for a type. What is that placeholder that I'm going to fill? The value that I'm using here is floating point, right? And it says that, okay, I'm going to fill wherever this quote is there, I'm going to fill it with floating point. So I'm expecting the first argument to be floating point and the rest of the list to be a floating point list, right? So this is a floating point. And the OCaml is going to check whether, so it has built up a constraint, right? You built up a constraint which says that because my first element is a floating point, the rest of the elements should also be floating points. But what type does OCaml infer for this one? It's a string list, right? Because this one is a string. And that is what OCaml is complaining here, right? It inferred that the list should be a floating point list, but it has observed that the value here is string. But the value expected is a floating point number. So just because it is generic does not mean you can put arbitrary types in there, right? It is sort of building it like constraint solving. So you have a single placeholder, you have a single variable, and if you infer a particular type for that variable, you sort of fill in the same type everywhere that variable occurs, right? So OCaml filled this with float, so the rest of the thing should be a float list, and that doesn't match here. And that's the reason for the error here. But the idea is that you can, if you use it in a context where you have the right kind of values, then everything works out. Okay, so let me now switch to the questions. So when we get a quote A, when we do not use an argument inside the function also, is it because that we cannot infer its type? I didn't understand the question, Sarthak. Can you have unmute? Yeah.
So am I audible?
Yeah, yeah.
I was asking that if we give a function as an argument, like in a function we have arguments, and we don't use one particular argument to
Yeah.
evaluate the expression inside. Like it's not
You,
useful.
yeah, it's not useful. So you don't particularly give it a type, or you've seen it in an experiment somewhere.
Yeah, I saw
So
this.
okay, yeah. So if you do let foo
Like
a b and just return b,
yes, sir.
right? I'm not using a. The type that is uh, let me do this. Okay, the type that is inferred. Actually, let's do. So I'm going to do b plus 1 for whatever reason. So I'm using b but not a, and the type is left to be filled in, right? So as you rightly point out, a is not being used. OCaml is placing no constraint on the type. It is just saying I'm just going to leave it as a placeholder. I think that makes sense. Does it?
Like, it's because we can't find its type. That's why it doesn't.
Yeah. So the better way to say that is the OCaml type inference is aiming to find out the most general type for a function, right? So it wants to identify what is the most general type. I can always say it is an integer or a string, right? But that will make it more specific. If I infer a to be an integer type, I cannot do foo of say 1.0 and then 1, right? You sort of rule out programs which you don't need to. And the point of OCaml is it's sort of type inference is trying to identify the most general type that can satisfy that particular function. So yeah, so that's why it's left as it is. Okay, so that's the first question. The second one is, do we require a symbol before nil? Anishwar Srivatswa. So Srivatsa Krishnan Ramalingam. So again, I don't get the question. So can you perhaps unmute and speak if you have, right?
Sir, do we require that or symbol before the? Because
no, actually, yeah, okay. So this is okay. This is just syntax, right? So this is not necessary. So you can have this, or you can just do this one. But the second one you certainly need. If you don't do this, then it will be a syntax error. Does that answer your question? It's just a syntactic convention. So you can do this. It will be free. It will be fine. Okay. Yes. So the third one, once we make a list of type int, it's yeah. So I think the third one is a good question. So I think I've already answered that. So once you make a list of type int, the quote A is filled in for that particular value, right? But you can still use cons in a different context. So essentially, I'm going to define L1 here, right, which is an integer list. I cannot mix int and string here. When I use cons again in L2, the use of cons here have nothing to do with the use of cons here, right? They are present in two different values. So obviously I can, sorry, I take back the word obviously. It is the case that it remains generic, right? So this cons is not constrained to be an integer. So it's still alpha. The cons here gets constrained because of the use of the values here. So that's why we had an error here when we sort of said this, right? Because the use of 1 here constrains the tail of the list to be an integer list, but it's not an integer list, it's a string list, and that's the error. Okay. So this is one of the, just to finish up what I was saying, this quote A is a type variable, right? We've seen variables in other languages. Variable is a name standing for an unknown value, right? When I write L1 equals something, it's a name for a value, right? A type variable is a name standing for an unknown type. So when I write quote A, quote B, and quote C in OCaml, I am actually just giving a name for a variable, and the names are going to be filled in with concrete types, right? So that's the analogy there. And this is not a concept that other languages don't have, right? If you've programmed in C++, if you use STL, you must have used something like std vector int or float or something, where you say this is a vector, and if you fill in the concrete type, it's a vector of integers, or it is a vector of strings, and so on. And in Java, we have similar ideas called generics, and in C# and other languages too, where you'd say something like list of t, right? Where t is a type variable that can be filled in with concrete types. And in OCaml, the type variables have to be preceded by this quote, right? And they can be of arbitrary length. So it doesn't matter what they are. So they are just alphanumeric conventions, right? Whatever conventions apply for regular variables apply there. You can have foo, key value, or useful names there. But we usually tend to use quote A, quote B because type variables don't appear often. They appear in a few places, but not as pervasively as regular variables because OCaml type inference just works usually. So you will never have to name these types. I will tend to interchangeably use quote A, quote B, and alpha beta for this one because pronouncing quote A is like quite a mouthful. So alpha beta is easier. And when I say alpha beta, think back to quote A, quote B, right? So I might use this interchangeably. Okay, so this generics and template instantiation and what we have with parameterized variance all tied to this idea called polymorphism, right? When we defined the data type quote A list, what we have defined is a polymorphic data type. What is polymorph? Poly is many and morph is change. So essentially, it is a data type that has many forms that can change, right? And polymorphism is a term that we tend to use often in programming languages. And the particular flavor of this polymorphism is known as parametric polymorphism. But I would sort of not dig in too deeply into this. I would just mention that um, if you've done the object-oriented analysis algorithm lab, right? OAIA lab, where you've studied the inheritance. That is also a type of polymorphism. That polymorphism is subtype polymorphism. So Java has multiple forms of polymorphism. It has subtype polymorphism, but also has parametric polymorphism. Parametric polymorphism is generics, essentially something like this, right? Or C++ template instantiation. OCaml also has both sort of polymorphisms. So OCaml has an object system as well. So we have subtype polymorphism. But parametric polymorphism is what we use pervasively, right? So this is something that we will use so pervasively that we won't even name it, right? We will just say this is something and we'll start using it. And it gives a lot of power. So as we will see, we can the cost of the syntactic cost of writing down parametric polymorphism is so low that we won't even explicitly name it. You'll just get used to what it means, and it sort of is quite easy to follow as well, right? And this sort of polymorphism, which is a parametric polymorphism, is related to Java generics and C++ template instantiation. Okay. So the last thing that I want to say is we have two components here, right? We have this quote A, which is a type variable. So what is this LST? Does it have any special significance? Yes, it does. This LST is a type constructor. So we've seen value constructors here, right? When I write nil or cons, these are value constructors. When I write cons, it's a constructor that takes 0 arguments. So it's just a constructor. Here is a constructor that constructs a value. Cons is a value constructor for the type alpha list, right? That can be used to construct values of type alpha list by passing two values, right? First one is alpha, second one is an alpha list. So cons is a value constructor that constructs values, and list here in alpha list is a type constructor, right? That constructs types such as int list, string list, shape list, and so on. So we don't manipulate these two constructors, the value constructors and type constructors, in the same way, but they are sort of fitting the same rubric in the sense that just like value constructors allow you to construct new values, type constructors allow you to construct new types. So here is different uses of LST to construct different types. Okay. Yeah, okay. So now that we've seen our own implementation of list, OCaml has a built-in support for list, right? and that list is nothing but just the list we've seen, right? Just to remind you, we just saw the implementation of list here, right? The list type here with nil and cons. OCaml uses the exact representation, but it just uses two different constructors, right? So just for syntactic convenience, in where we use nil, we use this open square brackets, close square brackets, right? That refers to the nil constructor, right? And we use these double colons for cons, which takes a value, right, and takes the tail of the list and constructs a new list where the value is the head at the head of the list. Okay, so this is just a special syntax, right? These two are just special syntax. Whenever you see this, you can just think about nil and cons. There is a bit more syntactic magic here. I'll explain what it is. So nil would be quoted list nil, right? And similarly, when I use this would be of the inbuilt type quote list list, which is the inferred type, right? And I think this relates to the answer that I gave Sarthak, right? So the type that is inferred for this empty list is a quote list. So we leave it as quote because it's the most general type that we can derive, right? That's the most generic one that we have. But I can always specialize it, right? Just to give you a flavor of what you can do, I can always say this is a int list, and that will also work. So think about these as constraints, right? That slot is not filled in, and by using, so recall that this is the syntax for doing explicit typing in OCaml. You can just specify a type for something. You can just say this expression has type int list now, and because alpha is a placeholder, int gets filled in there, and the type now for x is an int list. Of course, you can't fill in arbitrary things here, right? This won't work because x is an integer. This is a list that will not unify. Okay. Yeah, that's the thing about this. And just like we had cons2 of nil, you can do the same thing here. It constructs a list 1 to empty. And this is the other syntax OCaml allows you to write lists. So you can write open braces 1 semicolon 2. Again, semicolon is a OCaml quirk. In other languages, you would have, in Python-like languages, you would just use comma, semicolon for whatever reason. OCaml is 25 years old, right? So this is older than before we established these conventions. So so we use semicolon, get used to it. You'll often make a mistake where you use comma, but use semicolon. So, okay. And you can write the list, this list here also as 1 semicolon 2. That will be the same list. So this particular construction, this open square bracket 1 semicolon 2, is defining the exact list as this one, right? So OCaml compiler, the first step it does is it rewrites this one to something that looks like this one. Okay, this is just syntactic sugar. Makes it easy to write list-based programs. So OCaml has a special syntax. There is not much special syntax in OCaml. I tend to introduce a few things now, but yeah, the magic syntax will die down, right, in a few lectures, and we'll just get comfortable with what we have. Okay, this colon is right associative, right? So only then it makes sense. When you read 1 double colon 2 double colon empty list, you read it as 1 double colon 2 double colon empty list. What it does is a construction. So the way to read it is you have an empty list and you construct a new value which has 2 as the head and empty list as the tail, and then you construct a new list now with 1 as the head and this list as the tail, right? So again, this is pretty printed as 1 semicolon 2, but it's the same thing. Okay. Okay. We've done lists. We can do other types. So here is a definition of binary trees in OCaml, right? And I want the tree to be parameterized by arbitrary types. So I define the type to be a quote tree, right? Where quote is the type of the value that is stored in every node. The tree has a leaf node that is not parameterized. That's the leaf, right? And it has internal nodes where you have a left subtree, the value, and the right subtree, right? And in OCaml, this is the way of writing comments. So brackets, star, comment, close bracket, right? So this is just brackets, comments. And this constructs a tree, right? So now you can define these arbitrary tree types now. You can, if you want, yeah, so this is just a way of constructing trees. I think this should be fairly obvious. So this would be very similar to something that you would do in structures in C, right? Where you have a, where we don't explicitly name nil. And there is a very important reason for that. I will just come to that. But we will define a node which has 3 elements: left, value, data, and right. And we are doing the same thing here. Okay, so here is an example. Oh, I didn't run this. So here is an example. So, and again, so this is a tree which has at the root 0.0, left is leaf, right? Right side has a tree whose root, whose value is 1.0, and its 2 children are leaves. Okay, and the type is automatically inferred. So yeah, so just that I hinted, right? So in C, you just write the node data type, and wherever you have leaves, you will just use null, right? And OCaml doesn't have null, right? And Sir Tony Hoare is the person who founded a lot of made a lot of contributions to computer science as a field. So he invented program verification, right? The way you sort of prove that my program does certain things. He also invented quicksort, right? And he's done a bunch of things. He's still very active. I think he's 85 plus old. I've had the pleasure of meeting him in Cambridge, and he's still very actively thinking about this. But this is what he said about null. He invented null, right? I think it's probably useful to read through the entire thing. So he said, I call it my $1 billion mistake, null. It was the invention of the null reference in 1965, at the time when I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all of the references should be absolutely safe, right? That's the goal that he had, with checking performed automatically by the compiler, right? But I couldn't resist the temptation of putting in a null reference simply because it was so easy to implement. Null is just 0 value, right? It was easy to implement. This has led to innumerable errors, vulnerabilities, system crashes, have probably caused $1 billion of pain and damage in the last 40 years. And the cost is only increasing, right? So if you sort of think about a lot of the memory errors that we have today, all of these are security errors, right? And we spend billions and billions of dollars just fixing these bad security bugs. If you're someone who has inclination for security, Microsoft recently, they've also done it previously, but recently released a report where they say like 57% of identified security vulnerabilities are due to memory safety errors. So these are something like buffer overflows and not checking whether something is a null and accessing things that are used after free and all these bugs, right? These contribute to 50%, 57% of the observed security errors, right? Whenever you see a memory error, you sort of have to sort of link it directly to a security hole, right? And Rust is this new kid on the block, right? Actually, I mean new kid, but it's also 10 years old. So Rust language was developed with the explicit goal of not having these null pointer and memory safety errors, right? It is meant to be as efficient as C and C++, but it was designed to avoid null. So the focus of OCaml is different, and in OCaml we don't have null, right? There is no null, so you will not have to worry about segmentation falls due to accessing null pointers, right? That's not a thing that we have. Instead, what we have is we have explicit variance where which correspond to null values. So the null value here is a leaf. We explicitly name it, and the null value in the linked list is this null constructor, right? So this null constructor. The utility of this is sort of we'll have to see the next lecture to see how it prevents the null pointer errors to not occur. But I think that's the intuition there, right? Whenever we want to say something is a node or nothing else, we will always have an explicit constructor. We will never say it is a null value, right? So that is not something that OCaml has. So if you want to encode this idea, right? This idea of it is possible that some value is a valid value, or it may be null. So OCaml has a built-in variant, right? So again, this variant is not complicated. It is just the variant that I described here. It's called an option, right? And the type option takes a parameter, right? Type parameter is alpha. It has two constructors. One is none, so which just says the value does not exist, right? And the other is sum, and sum of this value. So the way to think about this type is it's a box, right? And the box can either be filled or empty, right? If it is filled, then the label on the box is going to say sum, right? It's going to say sum, in which case if you open it, you will see the value, the actual value, which is the alpha. Otherwise, it is going to say none, right? The box is going to say none, but the box will not allow you to open it, right? So because it is none, there is nothing inside it. We don't carry any value, right? So we use the option type whenever we want to sort of say this particular value can either be whatever concrete value that you can think of, but can also not exist. In that case, we use none. Yeah, so here is some examples just to brush up this thing idea. So when you use none, you get an quote option because OCaml again infers the most generic type. So it is of type option. We have quote option, and you can do sum 10, in which case you get int option. So int option type says that it's a box which contains an integer, right? The box is constructed with the sum constructor, and the value is 10. And similarly, you can use sum hello, right? So that constructs a box with hello in it. So when do you actually use option types, right? So here is a very simple example. Suppose we are modeling student information as records, right? So you can sort of think about the whole database as a list of these student records, right? Each student has a string, a roll number, which is also a string, and marks, final marks, which is an integer, right? So this particular schema looks fine, but I fill the database with the values at the beginning of the semester when the exam has not happened, right? But what is a good default value for marks? The marks is an integer, right? So of course, 0 is not a good answer because the student may score 0 or be absent for the exam or something, right? So you don't want to fill in 0. You can use -1, but the sort of breaking the invariant, right? When you conduct an exam, you're sort of conducting it where you say the marks can be anywhere from 0 to 100, right? But -1 is sort of this very ugly thing, right? Which you're sort of assigning meaning explicitly. Whenever I see -1, I'm sort of going to take it as, oh, the marks haven't been filled, right? This is what we do in C, right? If I were to do it in C, I would do -1. If I were to do it in, say, SQL, I will not write it this way in SQL, but if you were to have this particular schema, you would fill it with nil, right? But in OCaml, there is a better way to do it. So here is what you will do, right? You will say marks field is no longer just an integer, but an integer option, with the idea that when you initially populate the student table, you populated everything with none, and none signifies that it is not an integer, right? It's not something that is of type integer. It is a different type where it says the value of integer does not exist in the slot, right? It has not been filled in. So it's a better way of modeling these things, no camel. And you might sort of ask, what is the difference between this and using -1? And the answer to that will come in the next class. Okay. So here's a basic question, right? So some just to refresh all of the ideas. So given that we have variance, records, and tuples, which one would you pick for the following cases? So you want to represent currency denominations, which are 10, 20, 50, 100, 200, 500, and 2000. Which of these three things would you use? Would you use a record? Would you use a variant, or would you use a tuple? Any answers? One answer is record. Yeah, okay. Beautiful. So all three answers, which is great, but I think my answer would be variance, right? Why? I'm sort of okay. So I'll use variant, but I think I have the other answers as well. So students who have name and roll number, obviously, we just saw this here, right? We can use the record. And third one is, imagine you're building a dessert, right? And the dessert has multiple components. It has a sauce, it has a creamy component, and it has a crunchy component. You can build different desserts with filling in three different things. So there are three options, but dessert needs all three. So it is also obvious that you can use a tuple, right? That's fine. But you can also use a variant record. So here is what I've written down, right? So for currency denominations, I just want to represent the different sort of currencies, right? So I will use a variant here, right, where I use type denomination, and I'll use D10, D20, D50 up to D2000 to represent different currencies, right? So if I have, say, 10 currency notes, I want to compute to say that sum of these 10 things, I would say each one, like I would represent that as a list of denominations, right? So each denomination maps to an actual integer, but that's beside the point. To sort of say, you don't want to directly represent that with an integer, right? That would be bad because I can represent -1, for example, as a denomination, but that's not a denomination that exists. I only want to name the ones that exist. So I would have it as a list of denominations. I will have a function which takes the denominations, converts that to an integer, and then sums it up if you wanted to. Right, that's the answer for that. Here I've used records for both the student and dessert, right? For student, I said name and roll number, both are strings. And dessert, I used sauce, creamy, and crunchy as the labels, and all three are string. But you could conceivably use tuples here. That's also fine, except that when you use records, you get documentation for free, right? These are sort of, you can think of these as documentations, and you can sort of access the fields by the labels. So both of these are strings, right? And if you just see string star string in a tuple, you need to know which one is the name, which one is the roll number, for example, right? But having it as a record makes it explicit. So you can just use a student dot name and student dot roll number rather than finding out which one is the name and the roll number. So here is my take on when to use tuples and when to use records. As I mentioned, we could have used tuples for 2 and 3, but generally you'll see tuples being used for local use cases, right? Imagine you have a function. All the functions we've written so far return one value, but if I wanted to return two values, I could just return it as a pair, right? If the values that I need to return are A and B, I can just say the expression evaluates to open bracket A comma B, close bracket, right? This will return a value, which is a tuple, I mean, it is returning a pair of values. So for local use cases, it is very convenient, right? But anywhere you have more semantic meaning, say I am representing a student or a desert or something, it is always better to use records, right? As I mentioned, records are like tuples with documentation for free. And in terms of efficiency, both are compiled exactly the same way. Right? The compiler is smart enough to compile records to have the same representation as tuples, but also have the same access time as tuples. Right? If I access a record with dot name, then it has the same overhead as accessing and indexing into a tuple. Right? So efficiency is not a concern here. So wherever you need to use records, and tuples are for local use cases. We will see, I mean, as we see larger programs, we will see the use of tuples, but I don't think it's important to look at these cases right now. Okay, so that was data types. I'll start. We have 10 minutes. Any questions on this one? Okay, so what I'll do is I'll continue with the next lecture, and then we'll stop in a little bit. And then, is there something with dynamic keys? We have hash tables and other things, so we will study some of them later. Yeah, so records are static because you define a type for the record. They're completely static. If anyone has used JavaScript, these are not similar to the record types in JavaScript, right? Where you can index it with arbitrary things. Yeah, okay. So now let's look at the next lecture. I think if I do this. Okay. So this was taken from previous year, but I'll change it to. Okay. So far, all I've told you, right, in the last lecture is how to construct things, right? I've told you how to sort of construct these new types of lists, but I never told you how to extract values from the list, right? We've seen a little bit of how to extract values from records by using the dot syntax, but that's only scratching the surface, right? And if you think about last lecture as just putting stuff inside boxes, inside bigger boxes, this lecture is going to be how do you open the boxes, take things out, right? If you think about the option type, I showed you how to construct an option type that has a value in it, how to pry it apart and extract the value, right? That's pattern matching. This is one of the most powerful ideas in OCaml, but also this idea is also present in other functional languages, right? Haskell has it, Rust has it, right? If you use Rust, you can use pattern matching. A few other languages have it. It's quite powerful. Let's see why. Right. So first, let's start with the syntax. Right. While the algebraic data types are a way to construct data, pattern matching is a way to destruct data. So take it apart. Right. So the way we do this is we match on the shape of data. Right. So by whenever we construct algebraic data types, we are sort of describing the shape of the data. So we pattern match on the shape of the data and then extract part of the data by naming them, right? So that's the overall idea. And the syntax is this. So syntax is we have a match keyword, some expression E with several patterns, right? P1, P2 to Pn. This arrow, like minus greater than arrow, and then some expressions. Okay. And these patterns could have variables. So they can name the components as ABC. And those variables are in scope in this expression. So you can use those variables here in this expression. So this is the overall general syntax for pattern matching. let's dig in a little bit, right? So whenever you define types, right? When I define the type quote list, I don't know why this is not syntax failure. Okay, type quote list equals empty list or cons of value and tail of the list. You're actually doing two things, right? You're first defining, actually three things. You're first defining a new type called list. You're defining the constructors, right? The constructors are this particular open square braces, close square braces, and the constructor cons. But you're also defining two different things. Those things are patterns, right? The patterns are exactly the same as constructors here, and they are the same in other data types as well. So what is a pattern? A pattern allows you to match with the constructor. Okay. So the pattern open braces, close braces matches with the open braces, close braces. You can have patterns where you have variables, right? So patterns can have variables. And I am using the pattern with variable h and t. H is the head and t is the tail, right? That's the intuition behind using h and t. This particular pattern can match with any uses of cons essentially. Okay, so if I try to match it with this particular value, this one is a value, this is a pattern, right? This is a pattern, this is a value. When I try to match with this pattern, um, so h binds to 2 and t binds to this empty list. Okay, I can also match it with this pattern, which is cons again. And of course, as I mentioned before, cons is right associative, right? So you read it as 2 colon colon open brackets 3 colon colon square brackets close brackets. So there is a head which is 2, which is matching with the variable h, right? Binds to variable h. And then the tail of the list, which is a singleton list with just 3, binds to t, right? And there is also a wildcard pattern which matches with any value. Okay, so there is a notion of patterns, there is a notion of constructors, and patterns can be used to match with constructors. How do we actually use this in practice? Right. So here is a very simple example. So I'm defining a function. Okay, the function is list status. That all it's going to do is if the list is empty, it's going to print a message called list is empty. And if the list is non-empty, then it is going to print the head value. Okay, and let's see how it is implemented. So the function is list status, takes a list as an input. We match the pattern list, right? I match L with, so list could be of two things, right? It could either be this empty list, or it could be a complicated series of recursive applications of cons. I only care about two cases. If the list is empty, then I print the string empty list, right? I'm using print endline here, which is a function in OCaml, which prints to the screen, right? And puts an endline character at the end. And if the list is non-empty, then it means that there is a head and a tail of the list, right? And I bind the head to H and tail to T. I'm using printf here. So just like C, OCaml has support for printf. They're mostly the same. There are a few differences, but let's not, I'll point it out whenever there is a difference. It is saying the list is non-empty and the head value is %dh, right? And printing a new line. And this percentage bang is a way of telling OCaml to flush the std out, right? So in C, you might have, when you used file descriptors, if you use them, you have to explicitly flush them out. So this format specifier sort of forces the flushing out. All it does is it makes sure that when I run this program, the output is visible on the screen. Okay. So a few important things are going on here, right? So first thing is pattern matching. That is probably the easiest bit. The second thing that happens is because I'm printing it as a %d, right, which is a format specifier for integers, this value h is inferred to be of type integer, right? So this is an integer, and because I'm constructing a list using that integer, this whole thing should be an integer list. And because I'm pattern matching with L, this thing should be an integer list. And hence, this function will take an integer list as an input, right? So that is how OCaml infers the type of this function to be integer list, and it doesn't return anything. So print is sort of going to do void here, right? So it is returning the unit type. So if I just run this, so I get int list, and if I run it on empty, I get list is empty, right? Because the function pattern matches the first pattern, prints list is empty, and the second one, it's already run. So it pattern matches with the h:t, right? So head is bound to the value 1, and the variable t, which I'm not using here, is bound to the list with 2 and 3 in it, right? And I'm not using it. You don't need to use it. But what I'm printing here, the list is non-empty and the head is 1, right? So this is how you sort of use patterns to deconstruct the type, right? So deconstruct the value. I'll stop here. Questions regarding this? Any questions regarding this function?
Sir?
Yeah.
Sir, in this, h can be 1 double colon 2 and tail can be 3 double colon nil,
Yeah.
right?
Yeah. So, yeah, you can match it like this. Double colon 3, something like this, right? Is that your question? Yes or no?
No, sir. That
Yeah, you can.
L with h double colon t, right?
Yeah. It used to be h double colon t, right? So h double colon t, and you are proposing I change it to something else? Or?
No, like will h always match with 1 only, or can it match with 1 double colon 2?
No, it will always match with 1 because the way you read this, right, is 1, 2, 3, something like
Okay.
this, right? So it is pattern matching this one, right? Okay. So what happens if we replace h with t in the print statement? It won't type check, right? That's the short answer. So if you do this, it expects. So why does it not type check? Because d is an integer, right? So t is expected to be an integer. But in this pattern, right, we know the right hand side is a list, right? So this is some value, but this is a list. List is not an integer. So that's what you're going to hear from OCaml, right? And OCaml inferred this type to be a list, but an expression of type int was expected, right? So that's what you get. You sort of have to work out how OCaml comes up with these types a little bit so that you can understand the type errors. But usually it is very precise about where the error is. You can just read this thing, right? Oh, %d, I'm using t, and t is certainly not an integer. Okay, so can we do h? Can we do? Yeah, you can. To give, yeah. So yeah, good question. So can we do let h equals? Yeah, you can do this. For example, it complains about something, right? I'll tell you about this exhaustiveness of pattern matching in the next class. But yes, you can do it. And now head is value 1, right? Head is matched to 1, tail is matched to this one. Why is there a unit value in the output? Because print is also an expression. Everything is an expression in OCaml, right? It happens to have some side effect, which is printing to screen, but it is also returning this unit value. So what is happening here is if I just do print end line, if you want to know the type of something, you can just type it like this, right? Just type the function name. It will tell you it is a string to unit function. It is magically consuming string, right? And where does a string go? It is actually going to the output, but it's not returning anything useful. So that's why you see a unit value at the end. Really good question, Naman. Yeah, everything has to return a value. Okay, so any other questions? No questions? Okay, so I think we'll stop here. And then we can continue on Monday. Bye-bye.